This is 2.4, structure of metals and alloys. And your outcome is I can represent a metallic solid and or alloy using a model to show the structure and interactions present in the substance. So some properties of metals, they're shiny, they're malleable, they're ductile, and they're good conductors of heat and electricity. Nonmetals generally do not have these properties. So the fact that there's such a big difference in the properties between metals and nonmetals suggests that the structure, which is due to bonding in these two types of materials, is different. So bonding in metals is different from both covalent and ionic bonding. In covalent and ionic interactions, those electrons are localized. They either share electrons between two atoms or one atom gives an electron to another. In metals, instead, we have a delocalized model for the electrons. So the valence electrons are delocalized over several metal cations. So because those electrons are not tightly bounded to an individual atom, they're able to freely flow through the structure of the metal. So you can imagine that the metal cations are locked in place, surrounded by a sea of free-flowing, free-moving valence electron. So there is a force of attraction between the metal cations and the sea of electrons that holds together the metallic bond. So here we have some properties for metals and nonmetals. So explain how the electronegativity can be used to predict whether a pure substance is a metal or a nonmetal. So elements with low electronegativities are metals. These are going to easily lose electrons. Higher values are for nonmetals, which easily attract electrons. So because metals have low electronegativities, their electrons are loosely attracted to the nucleus. So this means they can very easily form this sea of free-flowing electrons. So electricity is just the flow of electrons from one place to another. Why would metals be good conductors of electricity, whereas covalently bonded compounds are not? So metals have low electronegativity values, whereas nonmetals have high values. So that is to say that metals hold on to their electrons loosely, and nonmetals hold on to their electrons strongly. So this is again because of the type of bonding that is present. So in a metal, we have those cations that are attracted to the electron C. And because those electrons are delocalized, they're able to move and flow, which is why metals are good conductors. Those electrons can move that energy from point A to point B because they're already mobile. So alloys are mixtures of metals or perhaps metals and other elements. This is done to give the alloy very specific properties. So for example, copper is combined with gold to create rose gold. It has a different color and it's much stronger than pure gold. So you don't find pure gold jewelry because gold is very soft and very malleable. So if you had a pure gold ring on your finger, in your day-to-day life, you would bang that up and dent it out of shape because it's very soft. So instead, the gold is alloyed with another metal or another element to make it a lot harder and stronger so it retains its shape. So looking at these two diagrams, or these three diagrams rather, what is the difference between an interstitial and substitutional alloy? So in a substitutional alloy, some of those metal atoms have been replaced with another metal atom of similar atomic radius. In interstitial alloys, smaller atoms are occupying the spaces in between the larger metal atoms. So here is some iron and some stainless steel. So stainless steel is an interstitial alloy. It is made of iron, chromium, and carbon. And they have slightly different arrangement, slightly different structure in stainless steel than we have in pure iron. So the atoms are arranged differently, which leads to different interactions between them, and that causes different properties. So which of the following is going to be more malleable, softer? Probably going to be that pure iron. Those atoms can easily slide past one another. So in metals, bonding is said to be a delocalized sea of electrons. How is this different from an ionic or covalent bond? So in ionic or covalent bonding, we have localized bonding. The electrons stay in one region of space. In metals, we have delocalized bonding, and those electrons are able to flow and move freely. So because we have this different structure between these types of compounds, we see very different properties. The second one is to compare interstitial and substitutional alloys.